So good evening everyone. I am Shivani Dhok and I welcome you all for the week 11 tutorial for the course of digital signal processing and its applications. So like every week, this week's tutorial will be divided into two parts. First, I'll have a brief recap of whatever was covered in week 11, followed by the questions which are related to the content that is covered in week 11. At any point of time, if you have any queries regarding what I am solving, please unmute yourself and ask those doubts. Don't put it in the chat box. I may not be able to see the chat box every time, so it's it's advised that please unmute yourself and ask your queries. If you have any queries or if you don't understand any step of the question that I am solving, please stop me then and there and ask your questions. Please don't wait till the end of that question. It will help you understand whatever I am solving in a better way. With that, let me quickly start with the recap of week 11 content. So, in week 10, we started with discussion related to realization of systems or realization of filters. Now, this filter realization, in the last lecture, we saw two forms. One was direct form 1 and direct form 2. So, those are the two forms which we can use to realize any filter with less number of resources or in an efficient way. In this week, we then looked at three more structures. The first one is cascade structure, next is cascade parallel structure, and another one is a lattice structure. So the first one that we discussed was known as a cascade structure. So for cascade structure, what do we have? If the system response h of z, I can write as h1 of z and h2 of z. And suppose I have blocks or realized blocks for these. So now what I can do, I can connect these two in parallel, in cascade form, that is something like this. And this equivalent will be simply my h of z. For cascade parallel structure, what do we have? So now suppose I am able to write my system response h of z as h1 of z, h2 of z plus h3 of z. Then this system I can realize it in this form. Can have h1 of z, then I can have h2 of z, and then I have here h3 of z, and this gets added here. So here is my x of z, or let's say x of n, and here I'll give my y of n, or let's say y of z. So this part here, is realized in a cascade form, and this total, this part is known as parallel realizations. You have connected this and this in parallel, similar to our circuit theory thing. So this part and this part is connected in parallel. These two are connected in cascade. That's why this particular realization method is known as cascade parallel structure. And the last thing that we discussed was this lattice structure. And this lattice structure I won't explain now because I have a lot of questions to cover today, a lot of lengthy questions to cover today, but we'll look at this lattice form with the help of examples. Mostly towards the end of this lecture, we'll look at this lattice form with the help of examples. Okay, any questions till this point? Okay, if there are no questions, then let me move on to the first question that I have planned to cover today. Okay, so the first question here says that there is a degeneracy in the system if at any stage the lattice parameter kn takes the value, and we have these four options, and this is a multiple correct answer type question. Okay, so how do we do that? Now, in order to understand this degeneracy, what we will look at is the backward step. Okay, so the backward step is given by just a moment. Yeah. So the backward step is given by an minus 1 of z is equal to an of z minus z to the power minus n kn into an z inverse divided by 1 minus kn square. Now, if you observe this equation here, when will degeneracy occur? Degeneracy will occur when the denominator is equal to 0. So, let me write that. Degeneracy will occur when the denominator of an minus 1 of z is 0. That is 1 minus kn square is equal to 0. So what do we have? We have 1 minus kn square is equal to 0, which means that kn square is equal to 1. Now this kn is a real number. Okay. So what does this notation mean? This means set of real numbers. This is a realizable system. So this has a these kns or these coefficients are real. So therefore this kn square is equal to 1. Therefore this kn can be equal to plus minus 1. Okay. So what do we get? Therefore if kn is equal to plus minus 1, then there will be a degeneracy in the system. So for k equal to plus minus 1. So for k equal to plus 1 and k equal to minus 1. So these two are our correct options, plus 1 and minus 1. Is it clear? Is this question clear? Any queries? Okay, if there are no queries, then let me move on to the question 2. So the question 2 here says that for the nth stage system function, an is defined as. So this we have seen in the lecture. So by definition, an of z is En of z divided by E0 of z. So therefore, if we look at the options that we have, the correct answer is this one. These are simple questions which were there in, this is last year's assignment. This is by definition. There is nothing that I have solved or discussed in a deep, something different. There is nothing different that I have discussed in this particular part. Okay, let's move on to the next question. It was a simple one. Still, if you have any queries, then let me know. Okay, so this question says that which of the following are valid cascade realizations. So we need to look at valid cascade realizations of the system yn equal to 3 by 4 yn minus 1 minus 1 by 8 yn minus 2 plus x of n plus 1 by 3 x of n minus 1. So we need to figure out from the given four options which one is a valid realization or cascade realization for this particular system. So in order to do that, first we should know the transfer function or the system function. Okay, so let us try to get that. So what is the difference equation given to us? We are given y of n is equal to 3 by 4 y of n minus 1 minus 1 by 8 y of n minus 2 plus x of n plus 1 by 3 x of n minus 1. Now what I will do now is I'll collect all the y terms on the right hand side and all the all the y terms on the left hand side and all x terms on the right hand side. So what do I get? Therefore we have y of n minus 3 by 4 y of n minus 1 plus 1 by 8 y of n minus 2 is equal to x of n plus 1 by 3 x of n minus 1. What we will do now, we will take the z transform. So taking z transform gives us the z transform of y of n is y of z minus 3 by 4 as it is. Z transform of y of n minus 1 is z inverse y of z plus 1 by 8 will remain as it is, and z transform of y of n minus 2 is z to the power minus 2 y of z, which is equal to z transform of x is x of z plus 1 by 3 z transform of x of n minus 1 is z inverse x of z. This is from the time shift property of z transform. So now I can take this y of z common. Then I have 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2, which is equal to x of z I can take common from right hand side, and inside the bracket I'll have 1 plus 1 by 3 z inverse. So therefore I have y of z upon x of z, which is our transfer function h of z, as 1 plus 1 by 3 z inverse divided by 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2. Okay, so now what we can do? So what we have obtained now is h of z is equal to 1 plus 1 by 3 z inverse divided by 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2. Now if you observe carefully, all of these are factors or denominators are having power as 1. Z inverse has powered 1 in all these denominators. So first, in order to find that cascade thing, what we will do is we'll factorize the denominator. So for that, we have 1 plus 1 by 3 z inverse in the numerator as it is, 1. This minus 3 by 4 I can write as minus 1 by 2 z inverse minus 1 by 4 z inverse plus 1 by 8 z to the power minus 2. So this is equal to 1 plus 1 by 3 z inverse divided by 1 minus 1 by 2 z inverse minus 1 by 4 I can take z inverse, I can take out common, 1 minus 1 by 2 z inverse. So this comes out to be equal to h of z is equal to 1 plus 1 by 3 z inverse divided by 1 minus 1 by 2 z inverse into 1 minus 1 by 4 z inverse. Is it clear till this point? Okay. So now let me write this down here. This h of z comes out to be equal to 1 plus 1 by 3 z inverse divided by 1 minus 1 by 2 z inverse into 1 minus 1 by 4 z inverse. Now since it is in cascade form, this should be equal to h1 of z multiplied by h2 of z. So now the systems h1 and h2 when productified give this transfer function that will be the answer. So let us start with the fourth option. So what do we have here? If you multiply these two, what we will get? We'll get 1 minus 4 z inverse divided by 1 minus 1 by 2 z inverse into 1 plus 1 by 3 z inverse, which is not equal to this. So if you look at only the numerator, that itself is different. Forget about the denominator. So option 4 is not the correct answer. So this is not the correct answer. Now if we look at option 3, again when we multiply these two, this one and this one, then what happens? This 1 plus 1 by 2 z inverse is there in the numerator, but here we have 1 plus 1 by 3 z inverse. So again this option is wrong. Similarly in option 2, when we multiply these two, what do we get? We get again 1 plus 1 by 2 z inverse in the numerator, which is not the case that we have. So now we are left with the option 1. So in the option 1, if we multiply h1 of z into h2 of z, what do we get? In the numerator, we will get 1 plus 1 by 3 z inverse, that is there. Along with that, in the denominator, we will get 1 minus 1 by 2 z inverse multiplied by 1 minus 1 by 4 z inverse. So that is exactly the same thing that we have here. Therefore, the correct answer or the correct option that we get is the first one. Is it clear? Okay, if there are no questions, then let me move on to the next question. Yeah, okay. So this is the question number 4. It says that consider a two-stage lattice filters cascaded together. So what we have two-stage lattice structures cascaded together. The first stage lattice has a constant K1, which is put ahead of the second stage of lattice with constant K2. Okay, the output from the first stage lattice filter, given the output of the first given the input of the first stage is x of n. So what is said is we are giving the input in the first stage of the lattice and we are taking out the output from the second stage lattice. So this is like an FIR filter what we are having. This is the nature of the lattice that we get in FIR filter. So the input that we are giving to the first stage of lattice is taken from the leads to an output from the second stage of lattice. So what we want to find is, we want to find this output from the second stage of lattice. Let me name it as something. Let's say it is y of n in terms of this x of n. Okay. Now in order to understand that, let us first draw the lattice structures. So let us first draw the stage 1. So let me draw the stage 1 first. So here, this one here is my E0. This is my E0 tilde. And then this x of n is given here. Like this. And then the same x of n is given to first stage E0 tilde as well. Now this goes here, and then what we have a K1 coming like this, and we have a K1 going like this, and we have one thing here, and we have a Z inverse here, and this also goes like this. And these two here are E1 and E1 tilde. Now this particular thing that I have drawn here is the stage 1. And let me say, in terms of time domain, let's say this is f1 of n and this is f2 of n. Sorry, f1 tilde of n. Just for the sake of notations. In time domain, this E0, 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 E0 tilde, E1, E1 tildes, these are Z domain representations. Now this is the time domain, this is the stage 1. Now let us draw the stage 2. So for stage 2, let me first draw these things. Like this. Then again we have a Z inverse here. Then this goes like this here. We have these coming like this. Then we have a K2 here. Then we have a K2 going like this. These go like this. And after that, what we get here at this end, we get E2. And here we get E2 tilde. And we take the output as our E2. So here I get my Y of n. And this is my stage 2. Okay. So now let us try to get our Y of n. So this Y of n depends on my f1 and f1 tildes. Okay, so let me just focus on stage 2. So what I'll do, first focus on stage 2. What do we get? We have Y of n. This Y of n here, what is it? It is f1 of n as it is, plus we have f1 tilde that gets multiplied by z inverse. So we have f1 tilde n minus 1 multiplied by k2. So what do we get? We get f1 of n plus f1 tilde n minus 1 into k2. Okay. So therefore, y of n comes out to be equal to f1 of n plus k2 times f1 tilde of n minus 1. So this is my first equation. So now we have y of n in terms of f1 and f1 tilde. Now next thing that we need to do is, we need to figure out what are the values of f1 and f1 tildes, which in turn depend on k1 and e0 tilde, or rather x of n. Okay, so let us try to figure out first f1 of n. Okay, so basically now for this, what we will do, we'll now focus on stage 1. Okay, so now let us first figure out what is the value of f1 of n. Okay, so this x1 goes here as it is. Okay, so we have this x of n coming here. At the same time, we have this x of n coming here and getting delayed. So at this point, we have x of n minus 1, and that x of n minus 1 gets multiplied by k1. So what do we have? We have x of n plus x of n minus 1 into k1, like this. That is equal to our f1 of n. So we have f1 of n is equal to x of n plus k1 times x of n minus 1. Okay. In similar way, we have even f1 of tilde here. So what do we have? We have this x of n coming here that gets scaled by k1. So here first we get x of k1 x of n. At the same time, we have x of n that gets delayed, that is x of n minus 1, as it is coming here. So what do we get? We have x of n minus 1 here plus x of n into k1, like this. Okay, so this first part is x of n minus 1 plus x of n into k1. Okay, so therefore f1 tilde of n is k1 x of n plus x of n minus 1. Okay, so now this is equation 2, and let me number this as equation 3. Now we have f1 and f1 tildes in terms of x of n, and this y of n we have written in terms of f1 and f1 tildes. But now we want relation between this y of n and x of n. So what we will do? Now we will substitute this equation 2 and 3 in this equation 1. So let me write it down. Substituting equation 2 and equation 3 in equation 1, we get y of n is equal to f1 is x of n plus k1 x of n minus 1 plus k2 times we have f1 tilde of n minus 1. So n minus 1, we need to replace all the n's here by n minus 1. So what we get? We get k1 x of n minus 1 plus x of n minus 1 minus 1, that is x of n minus 2. So this is equal to, I'll collect the terms now. We have x of n plus we have k1 x into, sorry, k1 into 1 plus k2 x of n minus 1 plus k2 into x of n minus 2. So this is the final input output relation. Is it clear till this point? Any questions? So this is the final answer that we have. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay, just a moment. Okay, so this is question 5. It says that in the parallel realization of the cascaded architecture of the discrete system in the following figure, this figure, which is really in a bad shape, this h of z is written in a partial fraction form as something like this. Which of the following is are true? And this is a multiple answer correct question. Okay, so this is the system h of z that is given to us. What I'll do is I'll just zoom it and I'll overwrite this with a thinner pen so that it's readable. So we have x here. This x goes like this here. Then it gets delayed. Z inverse. We have a z inverse here. Then we have minus 0.25 here. This. Then we have a 2 here. Like this. And then this goes ahead like this, and then we have another system like this. Yeah, something like this. Then we have a 0, z inverse, this is 0.25. Like this here we have minus 0.2. This goes up here, and here we have our y. Okay, so this is the question that is given to us. These are two systems that are connected in parallel. This is the first system, that is, let's say, my h1 of z, and this is the second system, that is h2 of z. Okay, so now what we have that this h1 of h of z is h1 of z multiplied by h2 of z, but this they have written in a partial fraction form, something like this. Okay, but now let us first figure out what this h of z is. Okay, so if let me copy paste this part, the next page. Yeah, so this is the system that we are having. So now let us first find out what is h1 of z. So if we observe carefully, this is a direct form 2. Representation. So therefore, we had seen in the previous class how to directly get it from the thing. So this first part here corresponds to the denominator and remaining part corresponds to the numerator. Just focus on this. So in the numerator there is nothing, no scaling and all. So therefore it is simply 1. And in the denominator, what do we have? We have first z inverse that gets multiplied by 2. But here we have negative of it. So we have 1 minus 2 z inverse, and then we have in the denominator z inverse. Sorry. So here we have z to the power minus 2 into minus 0.25. So we have plus 0.25 z to the power minus. Okay, so this we have. And in similar fashion, if we look at the second system, that is also, let's say, that is h2 of z. This is also a direct form 2. Representation. And for this, we have the numerator part and the denominator part, both the parts. So let us first focus on the numerator part. h2 of z is equal to, so this part here on the right hand side, this corresponds to the numerator. So we have no scaling here, so this is simply 1. 1 plus 0.25 into z inverse. Okay, so we have 1 plus 0.25 z inverse divided by what do we have? We have, there is no scaling here, so it is simply 1. Then we have z inverse into 3, so that will be minus 3z inverse, plus we have, sorry, we have z inverse into 0.2, and there is a z inverse earlier also, so this is simply 0.2 z to the power minus. Okay, Now this h of z is simply h1 of z into h2 of z. So therefore h of z is equal to h1 of z into h2 of z, which comes out to be equal to 1 plus 0.25 z inverse whole divided by the first case's denominator is 1 minus 2 z inverse plus 0.25 z to the power minus 2. So we have 1 minus 2 z inverse plus 0.25 z to the power minus 2 multiplied by 1 minus 3 z inverse plus 0.2 z to the power minus 2. And this h of z is equal to this particular thing that we have here. So let me take a screenshot of this. I'll copy. So this h of z is equal to the h of z that is given to us. Okay. Now finding this thing here, or rather finding partial fractions of this is a little bit cumbersome. So what we will do, we'll use another trick. We'll try to represent this partial fraction form in a cascade form. So if you observe carefully, this denominator part here and here are same. Similarly, here and here the denominators are same. Okay. So therefore what we will do, we'll simply cross multiply these. So what do we get? We get a plus bz inverse multiplied by 1 minus 3z inverse plus 0.2 z to the power minus 2 plus c plus dz inverse into 1 minus 2z inverse plus 0.25 z to the power minus 2 whole divided by 1 minus 2z inverse plus 0.25 z to the power minus 2 multiplied by 1 minus 3z inverse plus 0.2 z to the power minus 2. Okay, now if you observe carefully, this part and this part, they are identical. So what does it mean? The numerator here is equal to the numerator here. So therefore what we can say is this part here, a entire thing here is equal to 1 plus 0.25 z inverse. So before equating, what we will do, we'll first simplify. We will first simplify numerator and then equate it to 1 plus 0.25 z inverse. Okay, so let us do that. So for that, let me just take up this thing. I'll copy paste. Let me do that from the next page. Yeah. So what do we get? We get something like this. So first part is we have a minus 3az inverse plus 0.2 a z to the power minus 2 plus bz inverse minus 3b z to the power minus 2 plus 0.2 b z to the power minus 3. Similarly, the second part will be, let me write it in a different color just to distinguish. Yeah. Okay, so this becomes c minus 2cz inverse plus 0.25 z to the power minus 2 plus dz inverse minus 2d z to the power minus 2 plus 0.25 z to the power minus 3. Now we'll collect the coefficients for each of the z power. So what do we get? We have here a and then we have c here. These are the only two constant terms. So we get a plus c here, then plus z inverse. What do we have? We have minus 3az inverse, then we have bz inverse, then we have minus 2cz inverse, and we have dz inverse. So what do we get? We get minus 3a plus b minus 2c plus d z inverse. Okay, and plus we have z to the power minus 2. So what do we get now? So this is this thing, green one. Now we have z to the power minus 2. So we have this 0.2a, then we have minus 3b, we have 0.25 here. Something is missing, 0.25d. No, no, no. Yeah. 0.25 C. Yeah, sorry, I missed C here. C here, and I missed D here. Yeah. And then we have one more term is remaining, and that is this minus 2d z to the power minus 2. So what do we get? We get 0.2a minus 3b plus 0.25c minus 2d. This one, and plus we have the last term, that is z to the power minus 3, which has only the remaining two terms, this one and this one. So we get 0.2b plus 0.25d is equal to, and this we will be equating it to 1 plus 0.25 z inverse. So 1 plus 0.25, let me write it properly. So this thing is equal to 1 plus 0.25 z inverse. Okay. Now let us equate the coefficients of z inverse, z to the power minus 2 on left, z to the power minus 3 on LHS and RHS. So what do we get? If we compare, we get, therefore, a plus c is equal to 1, which implies that we get c is equal to 1 minus a. Let me number this as equation 1. Yeah, equation 1. Then in similar way, the z to the power 3, z to the power minus 3 coefficient is 0. So therefore what we can write is 0.2 plus 0.25d is equal to 0. So this implies that my d is equal to 0.2 minus 0.2 upon 0.25b, which is equal to minus 0.8b. So let me number this as equation 2. Now let us focus on the remaining two things, that is the coefficient of z inverse and the coefficient of z to the power minus 2. Okay, so let me write it properly. So what do we have? So therefore we have minus 3a plus b minus 2c plus d is equal to 0.25. So we simply equated this part to this. So what do we get? Now what we will do, we'll make all of these equations in terms of only a and b. Okay, so minus 3a will remain as it is, plus b, minus 2c we can replace by 1 minus a, plus d I can replace as minus 0.8b, which is equal to 0.25. So here what do we get? After simplifying, we get minus a plus 0.2b is equal to 2.25. And let me number this as equation. Similarly, if we equate this, the coefficient of z to the power minus 2 to the coefficient of z to the power minus 2 in the right hand side, which is 0, what do we get? So therefore we now have what do we have? We have 0.2a minus 3b plus 0.25c minus 2d is equal to 0. So we can substitute 0.2a minus 3b as it is plus 0.25 into 1 minus a minus 2 into minus 0.8b, which is equal to 0. So what do we get? We get, if we look at these two things, 0.2a into minus 0.25a, we get minus 0.05a. Then we have here minus 3b into 1.6b. So that comes out to be equal to minus 1.4b. And then we have a constant of 0.25 that we can shift in the right hand side. So that is equal to minus 0.25. Now if I multiply on both sides, or if I divide both sides by 0.05, what I get is minus 0.05. What I get is a plus 28b, which is equal to 5. So let me number this as equation 4. So let me collect equation 3 and equation 4 at one place. So what we have, equation 3 implies minus a plus 0.2b is equal to 2.25, and equation 4 implies a plus 28b is equal to 5. Now if I simplify this, what do we get? We get here 28, we add this, then we get 28.2b is equal to 7.25, which means that b comes out to be equal to 7.25 divided by 28.2. If you use your calculators, this comes out to be equal to 0.257. Okay, similarly, okay, now we have b. So now this a can be obtained by 5 minus 28b, which is equal to 5 minus 0.257 into 28. And when we simplify this comes out to be equal to minus 2.196. Now what we have? We have a is equal to minus 2.196. Then we have b as 0.257. And what we need to do? We need to figure out the values of C and D, and that we can do using the equations 1 and 2. So what does equation 1 imply? Equation 1 implies C is equal to 1 minus A, which is equal to 1 minus 2.196. This comes out to be equal to 3.196. And similarly, equation 2 implies, what is equation 2? Equation 2 implies D is equal to minus 0.8B. So D is equal to minus 0.8B, which is equal to minus 0.8 into 0.257. This comes out to be equal to minus 0.2056. Okay, so what all things we have now? We have A, B, C and D. Now let's go back to our options. So these options are in this form. Now I'll just copy paste the take a screenshot of these options and paste it here. I'll actually add a new page and do it. Yeah, so these are the options that we have. And what have we obtained? We have obtained A as minus 2. Okay, let me write it down here. We have obtained A as minus 2.196. We have B as 0.257. Then we have C as 3.196, and we have D as minus 0.257. 0.2056. Now let us focus on all the options one by one. So let us look at this option A. So it says that A is less than 0. So since A is what we have A as minus 2.196, which is less than 0. So this option is correct. Now next option is floor of B is equal to floor of D. So now for this option, for this option, let us first calculate floor of B. That is equal to floor of 0.257. Floor means the greatest integer that is less than this particular number. So which is the greatest integer which is less than this number? That is equal to 0. And similarly, floor of D is equal to floor of minus 0.2056. Now the greatest integer smaller than this particular value is minus 1, which means that this value is not equal to this. So this is not a correct option. Next thing is floor of this option. Floor of C, which is equal to floor of 3.196. Now the floor of this number, that is the greatest integer less than this particular number, is 3. So again this option is wrong. It is not equal to 4. So this option is also wrong. And the last option is D is greater than 0. Okay. So here we have D is equal to D equals to minus 0.2056, which is less than 0. So this option is also wrong. So the only correct option that we have is the first one, that is A is less than 0. Is it clear till this point? Is this question clear? This was a lengthy question, and these kind of questions were there in last year's assignment, which means with high chances similar questions will be there in this time's assignment and or maybe in the coming exam, the final exam. Is it clear? Any questions? Is this question clear? Take a moment and go through the solution that I have just written down. Yeah. You can also try to do partial fractions and then get to this equation and then directly find A and B. Okay. If there are no questions, then let me move on to the 6th question then. Yeah, so now the coming questions will be a little bit lengthier, and we'll try to be slow and clear with the solutions. If you have queries at any point of time, just stop me then and there and you can ask. Okay. So this question here says that for the system below, find the parallel form representation. Okay, so now what we will do, we'll try to split it into two or three systems or a constant and system, two systems, and we'll try to do it. Okay. Okay, so let's start. So what is given to us? We are given h of z is equal to 32 plus 18z inverse minus 2z to the power minus 2 divided by 8 plus 2z inverse minus z to the power minus 2. Okay. Now what I'll do, from the numerator, I'll take 2 common. So what I have 2, I have taken common. So here I am left with 16 plus 9z inverse minus 2z to the power, sorry, z to the power minus 2 divided by, I have 8 plus 2z inverse minus z to the power minus 2. Now what I'll do, I'll try to play with the numerator of this system. Okay, and for that what we will do is something like this. We'll split it into two parts. Okay, so what we will do, we'll write this as 2, then this 16 we'll split it in two parts, that is 8 plus 8 plus this 9z inverse also I'll split it into two parts. One part will be 2z inverse and another one will be 7z inverse. So we get 2z inverse plus 7z inverse, and this minus z to the power minus 2 as it is, whole divided by 8 plus 2z inverse minus z to the power minus 2. So now if you see this 8, this minus 2z inverse, and this minus z to the power minus 2 is exactly the same thing that is there in the denominator. Okay. So now what I can do, I can write this as 2 into 8 plus 2z inverse minus z to the power minus 2 whole divided by the same quantity, that is 8 plus 2z inverse minus z to the power minus 2, plus I have 2 into 8 plus 7z inverse divided by 8 plus 2z inverse minus z to the power minus 2. These get cancelled, and what we are left with is 2 plus, I can take out 8 common. So I'll have, okay, let me do it in a simpler way. So what I'll have is, yeah, I'll divide the numerator and denominator by 8. So I'll have 2 into 1 plus 7 by 8 z inverse divided by 1 plus 1 by 4 z inverse minus 1 by 8 z to the power minus 2. So now this I can write as 2 plus 7 by 4 z inverse whole divided by, I can write this 1 by 4 as 1 by 2 minus 1 by 4. So this is 1 plus 1 by 2 z inverse minus 1 by 4 z inverse minus 1 by 8 z to the power minus 2. Now if you look at the denominator here, I can factorize this. So this part, this I can write as 1 plus 1 by 2 z inverse minus 1 by 4 z inverse out common. We have 1 plus 1 by 2 z inverse. So this I can write as 1 plus 1 by 2 z inverse into 1 minus 1 by 4 z to the power minus 1, like this. So now I can replace this in the denominator. So what do I get? So I get, therefore this h of z is equal to 2 plus 7 by 4 z inverse divided by 1 plus 1 by 2 z inverse into 1 minus 1 by 2 z inverse. Okay, 1 by 4, sorry. Yeah. So now we can still go one step ahead and try to use partial fraction method to represent this as summation of two single order filters. Okay, so what we can do is, now we'll just focus on this part. We'll just focus on this part for now. Let's keep that 2 as it is. So this part here, I can write as, we use a different color. Yeah, 2 plus 7 by 4 z inverse divided by 1 plus 1 by 2 z inverse multiplied by 1 minus 1 by 4 z inverse. It is equal to a divided by 1 minus 1 by 4 z inverse plus b divided by 1 plus 1 by 2 z inverse. Now if I cross multiply, what do I get? I get a into 1 plus 1 by 2 z inverse plus b into 1 minus 1 by 4 z inverse. Now if I equate the numerators on both the sides, what do I get? I get 2 plus 7 by 4 z inverse is equal to, or let me write this on the new page. So what do I get? I get numerator, that is 2 plus 7 by 4 z inverse, that is equal to a into 1 plus 1 by 2 z inverse plus b into 1 minus 1 by 4 z inverse. And now what we need to do? We need to find the values of a and b. So what we can do is, first we will substitute, or what will, instead of let z inverse is equal to minus 2. So what will happen? What we will get? We'll get 2 plus 7 by 4. Z inverse is minus 2, that is equal to a into 1 plus 1 by 2 into minus 2 plus b into 1 minus 1 by 4 into minus 2. So this gets cancelled and this becomes 0. Here this gets cancelled. So what do we get? Here we have 2 into 2, 4. So we have 2 into 2, 4 minus 7, that is minus 3 by 2. So minus 3 by 2 is equal to b into, here it gets cancelled, minus minus plus, and then we have 2 plus 1 divided by 2. So that is 3 by 2, which implies that b comes out to be equal to minus 1. Okay, so now we have the value of b. The next thing that we need to find out is the value of a. So for that, let z inverse to be equal to 4. Okay, so what do we get now? So therefore, 2 plus 7 by 4 into 4 is equal to a into 1 plus 1 by 2 into 4. This is equal to, plus b into 1 minus 1 by 4 into 4. This gets cancelled and this is equal to 0. So what do we get? This is 2. This gets cancelled. So we have 9 is equal to 3a, which means that a comes out to be equal to 3. Is it clear till this point? Any questions? Any questions till this point? What we have done, we have simply represented this particular thing that is present here, that I have highlighted in red. I have represented this in a partial fraction form, which is this form. Okay, so what do we get? Let me add a page. So we had our h of z as 2 plus, I'll just write it down again, 2 plus 7 by 4 z inverse whole divided by, I have 1 minus 1 by 4 z inverse multiplied by 1 plus 1 by 2 z inverse, and this I had written as 2 plus a divided by 1 minus 1 by 4 z inverse, and a came out to be equal to 3. So we have plus 3 divided by 1 plus 1 by 2 z inverse, and then we have plus b divided by 1 plus 1 minus 1 by 4. Yeah, and then we have plus b divided by 1 plus 1 by 2 z inverse, and here b came out to be equal to minus 1. So we have minus 1 upon 1 minus 1 by 4 z inverse. Is it clear till this point? Any questions? Okay, so now this is our h of z. Now what we will do, we'll divide it into 3 parts. Okay, so now I can write this h of z as 2 plus 3 upon 1 minus 1 by 4 z inverse. So this part is my first part, and let's say this is h1 of z. Then I have this as our second part. Let me say that this is h2 of z, and plus we have minus 1 divided by 1 minus 1 plus 1 by 2 z inverse, and this is my third part. And this I can say that this is my h3 of z. So my h of z is basically h1 of z plus h2 of z plus h3 of z. Is it clear till this point? Now what we will do? We will realize this one by one. Okay, so we'll use this equation to realize this one by one. So let us start with h1 of z. So for that, what I have this x of z here, or let's say x of n. So this first gets like this. So what does this mean? This simply means that my x of n is getting scaled by a factor of 2. So I have a scaling by a factor of 2. And this part here is nothing but my h1 of z. This part is clear? After that, we'll figure out we'll try to realize our system h2 of z. And that we will do using the direct form to realization. So first we'll realize the denominator, and then we'll care about this numerator. So for that, what we will get? We have something like this. Then this gets delayed by 1 unit. Or let me just take it a little bit ahead. Yeah, something like this. Then we come here. This gets delayed by 1 unit. So we have a z inverse term, and then we have a scaling here. We have a scaling here, and that scaling will be negative of this quantity, that is 1 by 4. So we have 1 by 4 here, and now this gets scaled by a factor of 3 in the numerator. So we have scaling by 3 in the numerator. So this part, whatever we have realized just now, this part here is nothing but my h2 of z. Okay, and now we need to realize the third part, that is h3 of z. So in the similar fashion, we'll realize h3 of z. So let me take this down. Then I have something here like this. And again, it is a single order thing. So this comes here. Then we can delay it by 1 unit like this. That is something that we have here, z inverse. And then we have this coefficient of 1 by 2. So now we'll scale it by the negative of this quantity, minus 1 by 2. And then this gets scaled. This gets scaled by a factor of minus 1. And whatever we have just realized is simply h3 of z. So this thing here is simply h3 of. Then what is my h of z? My h of z is simply addition of h1 of z, h2 of z and h3 of z. So let me take this here. Then this gets added like this. And then this further gets added like this. And this is my y of n. So what I get at this point, here I have h1 of z plus h2 of z. That system, I'm just talking about system realization. And at this point, okay, let me not write it like this, it's confusing. Okay, so here I am adding h1 of z and h2 of z, and that sum I'm adding here. So this is the cascade representation, parallel form representation of our given system. Is it clear at this point? Any questions? Okay. If there are no questions, then let me move on to the next question. Again, I'm so sorry for this kind of diagram. I'll just redraw it. But let me just read the question first. So it says that find the y of z divided by x of z. That is simply the transfer function in the following signal flow diagram. So if you observe carefully, this is a lattice type of structure. And what we have x of z here. Then this gets here, 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 like this. And then we have something like this. We have a feedback kind of thing. So this is an IIR realization and not an FIR realization. So I have a Z inverse here, Z inverse here, and this is my Y of Z. I have one here and minus one here. And then I have 2 here and minus 2 here. Okay, now we need to figure out what are these, what is y by x and y by y of z by x of z. So let us quickly finish off with the notations that we have for lattice. So this thing here, let me use a different color for that matter. Yeah, this thing here is E0 tilde. This is E0. Then at this point, this is E1 and E1 tilde. And here it is E2 and E2 tilde. Okay, so basically what we have from this figure, what do we have? We have x of z as our E2 of z. Okay, so now there are some standard equations for our lattice structure for this FIR realization. This is denominator realization of FIR. So by standard equations, which you can look up in your notes of your class, what do we have? We have En plus 1 of z is equal to En of z plus Kn plus 1 En tilde of z into z inverse. Similarly, En plus 1 tilde of z is equal to En of z, sorry, Kn plus 1 into En of z plus z inverse En tilde of z. Okay, so now what we will do, we have this thing here. We have E0 of z equal to E0 tilde of z equal to y of z from this diagram. So now what we will do, we'll first find out E1 and E1 tilde. So therefore, first we will find E1 of z and E1 tilde of z. And how can we do that? For that, we have E1 of z is equal to E0 of z plus K1 into E0 tilde of z into z inverse. Now E0 of z, we have seen that is equal to y of z. And if you observe in this diagram, my K1 is equal to 1. So what we get? We get it something like this. This is y of z plus K1 is 1 into y of z into z inverse. So now if I take y of z common, what I get? 1 plus z inverse. Okay. Similarly, this E1 tilde of z, using the equation that we wrote here, it is K1 into E0 of z plus z inverse into E0 tilde of z plus z inverse into E0 tilde of z. Again, E0 and E0 tilde is simply our y. So this is K1 and K1 is 1. So this is 1 into y of z plus z inverse into y of z. So this, again, I can take out this y of z outside. This becomes 1 plus z inverse. Okay. Now I have E1 of z and E1 tilde of z. So I have reached to this part of my lattice. Now I need to figure out my x of z, which is simply my E2 of z. Okay. So now what I have, next thing that I'll do is finding E2 of z, which is equal to x of z. Now this, I can just simply ignore E2 tilde of z because we are not interested in e2 tilde of z, because we just want x of z which is equal to e2 of z, and e2 tilde of z is nowhere used in that fashion, in that place. So now we'll simply find our e2 of z. So therefore x of z, which is equal to e2 of z, that is equal to again using this first equation that I have written here, it will be e1 of z plus k2 into e1 tilde of z, z inverse. So what I get is k, sorry, e1 of z plus k2 z inverse into e1 tilde of z. What is e1 of z? E1 of z and e2 of z, e1 of z and e1 tilde of z both are y of z into 1 plus z inverse. So I can write this as y of z into 1 plus z inverse plus k2. If you observe this diagram, my k2 is equal to 2. So plus 2 into z inverse y of z into 1 plus z inverse. Now I can take out common y of z into 1 plus z inverse. So I have y of z into 1 plus z inverse, and what I am left with is 1 plus 2z inverse. So what I have, therefore I have x of z is equal to y of z divided by 1 plus z inverse into 1 plus 2z inverse. Now I can divide both sides by x of z into 1 plus z inverse into 1 plus 1 plus 2z inverse. So therefore what do I get? So therefore y of z upon x of z, this comes out to be equal to 1 upon 1 plus z inverse into 1 plus 2z inverse. Is it clear? Any questions? Okay, so this is the final answer that we have. If there are no questions, then I'll just move on to the next question. Okay, again, similar kind of diagram. Let me just redraw it. So I have x of z here, then I have it going here and here on both the directions. Like this. Then this goes here. We have a z inverse here. Then we have this feed going here, like this, 2 and minus 2. And similarly, we have a thing going like this, coming down and like this, and it gets added here. And this is my y of z, and I have a z inverse here, like this. And if you observe carefully this particular question or this particular diagram, this is a parallel structure where this is the first system that I have, and this is the second system. Sorry, this is the second system that I have. Okay, so I can write this as, this is this red one, whatever I'm highlighting, this is my h1 of z, and similarly I have this part, sorry, yeah, the one which I have highlighted in green, and this thing here is my h2 of z. So this y of z upon x of z is simply h1 of z plus h2 of z. Now what is h1 of z? h1 of z can be obtained from this equation. Here it is simply z inverse. So therefore we have h1 of z is simply z inverse. And what is h2 of z? You observe this part carefully. This part. Observe it carefully. This green one which I have highlighted. Just observe it carefully and look at the question that we had, or look at the system model or system diagram that we had in the previous question. So let me go back there. If you see this particular equation, this particular figure, it is exactly the same signal flow diagram or same lattice structure that we had in this question 7. Okay, so this is just the same system that is connected in parallel with another system. So this green thing, h2 of z, is equal to the system equation that we have obtained in the previous question, which is 1 upon 1 plus z inverse into 1 plus 2 z inverse. 1 upon 1 plus z inverse into 1 plus 2z inverse. And why this is true? Since h2 of z is the same lattice as in question 7. Okay, so what do we have now? So therefore we have h1 of z as z inverse, and we have h2 of z as 1 over 1 plus z inverse into 1 plus 2z inverse. So therefore my y of z upon x of z, which is equal to h1 of z plus h2 of z, this comes out to be equal to z inverse plus 1 over 1 plus z inverse into 1 plus 2z inverse. Is it clear? Any questions till this point? This is the final answer for the system, for the value of y of z upon x of z. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay, so it says that how many unit delay elements will be required if we realize the given h of z using a parallel architecture with a lattice structure. Okay, so what it says is we have to realize this given system using the parallel architecture, and that parallel architecture should have a lattice structure. So now first let us figure out what kind of parallel structure we can have. Now in order to do that, just first look at this, just observe the transfer function that is given to us, and you look at the first term of this transfer function, and if you observe this part, and this is exactly same of what we have in the denominator. Okay, so now I can split this in this h of z into two summations or two factors. So we have h of z as 2z inverse into 1 plus 1 by 2z inverse into 1 plus 1 by 3z inverse whole divided by, we have 1 plus 1 by 2z inverse into 1 plus 1 by 3z inverse plus 1 plus 1 by 4z inverse divided by 1 plus 1 by 2z inverse into 1 plus 1 by 3z inverse. Okay, so this gets cancelled, and what we are left with is 2z inverse plus 1 plus 1 by 4 z inverse upon, I can simplify this will be 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. So let me write it again. So what do we have? We have h of z to be equal to 2z inverse plus 1 plus 1 by 4 z inverse divided by 1 plus 1 by 2 z inverse into 1 plus 1 by 3 z inverse. So now what we will do, this will be my h1 of z, and the second one, this one will be my h2 of z, and this h2 of z we will realize using lattice. Okay, so now the number of delays, the total number of delays that we will require will be equal to the number of delays required to realize h1 and the number of delays required to realize h2. Okay, so what we have, total number of delays is equal to delays for h1 plus number of delays that are required for h2. So now what do we have? Now if you observe carefully, this h1 is simply a 2z inverse. It's a unit delay shift that it is giving to the input. So therefore, what do we have? We have number of delays, or rather let me use the same notations. Delays for h1, number of delays for h1 is simply equal to 1. Okay, and now for delays for h2, and for a lattice structure, these delays for h2 are basically given by the degree of the denominator polynomial. So this is equal to the degree of the denominator polynomial. And what is the degree of the denominator polynomial? So this is a single degree thing getting multiplied by a single degree thing. So the total degree that we have is basically equal to 2, or what we have seen here, this comes out to be equal to, the degree comes out to be equal to 2. So this is equal to 2. So therefore, the total number of delays is equal to the number of delays required to realize h1, which is equal to 1, plus the total number of delays required to realize the h2, system h2, which is equal to 2. So this comes out to be equal to 3. Is it clear? Any questions? Any questions? Okay. If there are no questions, just a moment. Okay, if there are no questions, then let me move on to the last question that I have planned to cover today. This is one of the most important question that I wanted to cover today, and this is basically the realization of an IIR system. I'm taking IIR especially because it is little bit more cumbersome compared to FIR. FIR is easier compared to this. So what we will do is we'll realize this IIR system with the help of a lattice structure. Okay. So how do we do that? So we are given this h of z as 1 plus 1 by 4 z inverse whole divided by, we have 1 plus 1 by 2 z inverse into 1 plus 1 by 3 z inverse, and this I can write as 1 plus 1 by 4 z inverse, and I can simplify the denominator and get the denominator polynomial. So that will be 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. So in order to realize this IIR filter or IIR system using the lattice structure, what do? We write this h of z, which is equal to my 1 plus 1 by 4 z inverse divided by 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2 as summation m running from 0 to 2 cm into am tilde of z whole divided by a2 of z. So this I can also write as c0 a0 tilde of z plus c1 a1 tilde of z plus c2 a2 tilde of z whole divided by a2 of z. And what we will do, we want to realize this system, and for that we will use the repetitive structure of our lattice. Okay, and we have two steps in designing this particular system. Okay, so first step is realization of the denominator, and next step is realization of the numerator. So let us first start with the realization of denominator. So step 1, and this realizing the denominator is the main thing that involves designing of your lattice. Okay, step 1 is realization of denominator. Okay, and for this we will use the repetitive structure, lattice structure, let's say. Given on next page. Okay, so this repetitive lattice structure is something like this. We have seen it earlier, but let me just repeat it once. So we have E0, 2, 3, 4, something like this. We have En here. We have En plus 1 here. Then we have like this. We have En tilde here, and we have En plus 1 tilde here. And this is the flow, and this is the flow here in the bottom line. Then we have one line going like this. Here we have minus kn plus 1, and here this thing comes down. Here we have kn plus 1. Okay, so this is the repetitive structure that we will be using, and this kn, or rather this kn, this Kn is the coefficient of z to the power minus n in an of z. Okay, so now let us start doing this. So from this given transfer function, what do we have? We have a2 of z is equal to this thing that is in the denominator. So we have a2 of z as 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. So using this logic, what we wrote here, what do we get? We get k2 as 1 by 6. So K2 we have. Now after using K2, after getting K2, what we need to do is we need to figure out the next stage, which is for A1. And for that, what we will use the backward equation that we have. So we have, or we will use this, that is an of z is equal to an plus 1 of z minus kn plus 1 an plus 1 tilde of z whole divided by 1 minus kn plus 1 square. So therefore, I have a1 of z is equal to a2 of z minus k2 a2 tilde of z divided by 1 minus k2 square. Now what we have? We have, or we are given a2 of z as 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. So this a2 tilde of z is simply reverse polynomial. So we have z to the power minus 2 plus 5 by 6 z inverse plus 1 by 6. I will substitute these two things in our A1 equation. So what do we get? So therefore, A1 of z is equal to my A2 of z, which is 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2 plus, minus my K2. My K2 came out to be equal to 1 by 6. So this is basically a recursive procedure. It takes time, but it's a wonderful procedure. Then this is z to the power minus 2 plus 5 by 6 z inverse plus 1 by 6 whole divided by 1 minus K2 square. So now if you observe, this 1 by 6 z in z to the power minus 2 and this gets cancelled. This should happen. You should come up with a1 which is having a degree as 1. If this cancellation is not happening, then there is something wrong with your calculations. You need to recheck them. Okay, so now let us simplify this. What I'll do, I'll combine the constant terms. So I have 1 and then I have 1 by 6 here. So 1 minus 1 by 6 into 1 by 6. So I have 1 minus 1 by 6 square plus z inverse I have common. That will be 5 by 6 minus 5 by 6 into 1 by 6. So what I'll do, I'll also take 5 by 6 common. So I'll have here 1 minus 1 by 6 whole divided by 1 minus 1 by 6 whole square. So this is equal to 1 plus z inverse into 5 by 6 into 1 minus 1 by 6. The denominator I can write as 1 plus 1 by 6 into 1 minus 1 by 6. This gets cancelled and what we are left with is, so we have A1 of Z is equal to 1 plus Z inverse into 5 by 6 divided by 7 by 6. This gets cancelled. So this is equal to 1 plus 5 by 7 Z inverse. So now again using the same logic that my K1 will be the coefficient of Z to the power minus 1 in A1 of Z. So therefore what I get, so therefore K1 comes out to be equal to 5 by 7. Is this clear? Is this part clear? Now A1 of Z is this. Similarly, A1 tilde of Z will be Z inverse plus 5 by 7. Okay? Yeah. Okay. So now let us use the values of K1 and K2 to construct our lattice. So this is a degree 2 polynomial in the denominator. So only 2 delay elements will be there. Okay, I forgot to add a Z inverse here. Yeah, there is a Z inverse here. So let me take this, copy this, and I'll paste it here. Sorry, copy it properly. So what do I have? First I'll have an E2 here, and I'll have an E2 tilde here, and I'll have E1 here, and I'll have E1 tilde here. Similarly, I'll have a K2 here, and I'll have a K2 here. What is the value of K2 that we have? We had K2 coming out to be equal to 1 by 6. So this is equal to 1 by 6, and this is also equal to 1 by 6. Minus 1 by 6 and 1 by 6. Okay. So this is my stage 1 lattice. Now let us construct stage 2. Yeah. So for, sorry, this is my stage 2 lattice actually, to be precise. Yeah. Now I'll construct my stage 1 lattice. Okay. So now what I have here, I'll have E1 and E1 tilde, and I'll have E0 and E0 tilde. Okay, and this E0 and E0 tilde are same like this. And here I'll have K1 and minus K1 and K1. What is the value of K1 that we got? We got K1 as 5 by 7. So here I'll have minus 5 by 7, and here I'll have 5 by 7. Another thing to note here is this E2 will be equal to my x of z. Okay. So now let us construct the denominator. So final construction of denominator, and this comes out to be equal to, or this is given by, I'll just cascade these systems. So I'll take this and copy, and I'll paste it here. Just do something like this to save space. Take E1 here and E1 tilde here. Let me move it a little bit this side like this. Okay, and then I have this thing here, something like this. and this simply gets connected like this. So this is the realization of my, sorry, opposite direction. This is the realization of my denominator. Now denominator is done. Now what is remaining? Now the remaining thing is the numerator. So let us do the numerator now. So that is the final step. That is step 2. Realize the numerator. And how do we do that? For that we take up this system. Let me paste it here. Then we take this like this. We scale it by C0. C0. Then here, this is my even tilde. So this gets scaled by C1. And here I have my even tilde, E2 tilde. So this gets scaled by C2. Now these two get added like this. And then we have similar thing coming here. So these two also get added. And this is my final y of z. Okay, so now what is remaining is we need to find the values of C0, C1 and C2. So now we need to find the values of C0, C1 and C2. And for this we will use the numerator polynomial that we have. Okay, so let us go back to our our transfer function. So we have this. We have this equation C0, A0 till this, whatever we have in the right hand side, that will equate with the numerator of the left hand side. Okay, so what do we get? We have from the transfer function we have C0 A0 tilde of Z plus C1 A1 tilde of Z plus C2 A2 tilde of Z is equal to 1 plus 1 by 4 Z inverse. Now a quick homework for you is to show that this A0 tilde of Z is equal to 1. This is a simple exercise. This is the last stage of lattice. It comes out to be equal to 1. So just quickly try and prove it using the iterative formula that we had. So now what we get, C0 plus C1 into A1 tilde of Z. What is A1 tilde of Z? So this is what we got as our A1 tilde of Z. That is Z inverse into Z inverse plus 5 by 7. Plus C2, and we have A2 tilde of Z. What is A2 tilde of Z now? Yeah, A2 tilde of Z is Z to the power minus 2 plus 5 by 6 Z inverse plus 1 by 6. So we have Z to the power minus 2 plus 5 by 6 Z inverse plus 1 by 6, which is equal to 1 plus 1 by 4 Z inverse. Now if you compare both sides, there is no Z to the power minus 2 term here. So the coefficient of Z to the power minus 2 on the left hand side should also be equal to 0. So therefore we have C2 equal to 0. This is the first thing that we get. So now if we substitute C2 to be equal to 0 in this term is gone. Okay, so now what we are left with? we are left with C0 plus C1 into Z inverse plus 5 by 7, which is equal to 1 plus 1 by 4 Z inverse. Okay. So now if I compare the coefficients of Z inverse, we have C1 to be equal to 1 by 4. And in order to get the value of C0, we'll compare the constants on both the sides. So what we get, C0 plus the constant term C1 5 by 7, or let's say 5 by 7 C1, which is equal to 1. And C1 we have obtained as 1 by 4. So the C0 is equal to 1 minus 5 by 7 into C1, and the C1 is equal to 1 by 4. So now this comes out to be equal to 1 minus 5 by 28, which is 23 by 28. So what we have now? We have C0 to be equal to 23 by 28. Then we have C1 as 1 and we have C2 as 0. And now we will put these values in this system that we have to get the final system equation. So let me just take this, let me copy and let me paste it here. I don't think it will come. Okay, just keep it outside, something like this. So what we obtained this C0 as 23 by 28. Then we obtained this C1 here as 1, and sorry, not 1, 1 by 4, 1 by 4, sorry. And the C2 came out to be equal to 0. So there is no need of this branch here. So the output that we will get is directly measured from here, and this is my y of z. So this diagram, whatever I have drawn just now, is the final diagram or final realization of this system using the lattice structure. Is it clear? Any questions till this point? This was a lengthy question. I'll just go through the solution once more so that it is clear to everyone. So what this question was? The question said that we want to realize this following system function using the lattice structure. And this lattice structure that is given to, and the transfer function that is given to us is 1 plus 1 by 4 z inverse divided by 1 plus 1 by 2 z inverse into 1 plus 1 by 3 z inverse. So this is the thing. And we simplified its denominator to get something like this. And we wanted to realize this system, this IIR system, with the help of a lattice structure. And this we can write as something like this, that is summation m equal to 0 to 2 cm am tilde z divided by a2 of z, which simplifies something like this. Now in order to realize this h of z system, there are two steps. The first step is realization of the denominator, which includes the use of repetitive lattice structure, which is given like this, and after that we realize the numerator. Now, and in order to realize this denominator, what do we need? We need the value of this k's. And how to get these k's? These k's can be obtained, or rather the kn can be obtained by looking at the coefficient of z to the power minus n in an of z. So now in our system or in our transfer function, what are we given? We are given a2 of z. So this a2 of z is basically given as 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2, which is the denominator of our transfer function. So now we will compare the coefficient of z to the power minus 2 and we'll see what it is, and that will give us our k2. After that, now we have k2, we want k1 also. Now in order to get k1, what we will do? We will use this recursive equation that we have, and that is given by something like this, and we will now substitute our a2 of z and a2 tilde of z. Now a2 of z we had. How to obtain a2 tilde of z? So we have this 1 by 1, 1 plus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. So now this a2 tilde of z is basically a same degree 2 polynomial but reversed coefficients. So this here, this 1 will be the coefficient of z2 inverse, z inverse z to the power minus 2. Then this 5 by 6 will be the coefficient of z to the power minus 1, and this 1 by 6 will be a constant. So now we'll substitute these and simplify, and after simplification we'll get a1 of z, which should be a degree 1 polynomial. That comes out to be something like this. Now again we'll compare the coefficient of z to the power minus 1 to get k1, which comes out to be equal to 5 by 7, and a1 tilde of z is simply z inverse plus 5 by 7. Now after that, we use the values of k1 and k2 in the repetitive structure of lattice to get the final construction of our denominator. Now once we have our denominator, the next step is to realize the numerator, and that is given by this particular diagram here. Now this part is simply our denominator. We have already designed that. Now what remains to find these coefficients c0, c1 and c2, and we will use the numerator function of our numerator part of our transfer function to get the values of c0, c1 and c2. And when we simplify it, we get the value of c0 as 23 by 28, c1 as 1 by 4 and c2 as 0. And therefore, after substituting these values, this is the final lattice structure that we get. Is it clear? So this is the quick revision of what we have done in this last question. I repeated it because it's a little bit lengthy question and it is cumbersome to do. If you have any questions at any point in this, please feel free to ask. Okay, if you have no questions, then thank you for attending today's session. Hope to see you in the next week as well. Thank you.